Our galaxy hides worlds that defy every textbook on planetary science. You are about to journey to 35 planets with compositions so alien, they challenge our fundamental understanding of the cosmos. By the end of this exploration, you will know the secrets of worlds made of diamond, planets darker than black paint, and giants so fluffy they could float on water. We will uncover how a world could experience iron rain and what mysteries lie on a planet shaped like a giant eyeball. What does the night sky make you wonder about our place in the universe? The first world on our journey is a treasure chest forged in stellar fire. 55 Cancri orbits so close to its sun that a single year passes in just 18 hours. This proximity creates a world of unimaginable extremes. Its surface temperature soars high enough to liquefy iron, creating vast global oceans of incandescent lava that glow fiercely against the perpetual blackness of space. But the true marvel of this world lies hidden beneath its fiery skin. Scientists believe the planet is composed largely of carbon, the same element found in the graphite of your pencil. Under the immense pressures deep within the planet, that carbon is likely crushed into a crystalline structure, forming a layer of solid diamond that could be thousands of miles thick. This incredible hypothesis emerged from analyzing the starlight filtering through the planet's atmosphere. The technique, called spectroscopy, revealed a surprisingly high ratio of carbon to oxygen in the system, a clear signature of a carbon-rich world. The existence of a diamond planet immediately rewrites our expectations. It tells us that planetary systems can form from materials vastly different from our own solar system, where oxygen was more abundant than carbon. This single world proves that the universe can craft planets from the most unexpected of ingredients, turning a fundamental building block of life into a celestial jewel of almost impossible value. Yet a world of glittering diamond is not the only gem our galaxy has to offer. From a celestial jewel, we now turn to a void, a world of profound and absolute darkness. TRES 2b is a gas giant, a type of planet often called a hot Jupiter, but it holds a unique and unsettling title. It is the darkest world ever discovered, a planet that reflects less than 1% of the starlight that falls upon it. This makes it blacker than coal, blacker than black acrylic paint, a featureless abyss floating in space. Its composition is a deep and troubling mystery. Most gas giants in our own solar system, like Jupiter and Saturn, are wrapped in bright, reflective clouds of ammonia that act like cosmic mirrors, bouncing a significant amount of sunlight back into space. TRES 2b appears to possess no such reflective blanket. Scientists speculate its atmosphere might be filled with vaporized forms of strange elements like sodium and potassium, or perhaps it is choked with dark, light-absorbing chemicals that are completely alien to our earthly experience. The planet orbits so close to its star that its day side is scorched to a temperature of over 1,800 degrees Fahrenheit. This incredible heat creates a faint, menacing glow. The atmosphere itself glows with a deep, dull red, like a colossal ember, but this faint, intrinsic light is not reflected. It is swallowed almost entirely, making the planet darker than any known natural substance. It is a world that does not simply sit in shadow. It is shadow itself, a cosmic paradox of searing heat and absolute blackness. But the cosmos holds more than just dark jewels and diamond worlds. It also creates giants of impossible lightness. Imagine a planet larger than Jupiter, yet so light it could float in a cosmic ocean. This is not a fantasy. WASP-17b is one such world, a puffy gas giant with a density lower than styrofoam. Its vast atmosphere is stretched so thin that scientists are still puzzling over the forces that keep it inflated. One leading theory points to an internal heat source, a powerful engine deep within the planet that superheats its gases, causing them to expand to this extraordinary size. Another possibility involves its unique and retrograde orbit, a path where it moves backwards around its star. This strange dance could create immense tidal forces, churning the planet's interior and generating the excess heat needed to puff it up like a hot air balloon. It defies our basic expectations of how a planet should behave, a colossal yet fragile bubble of gas held together by mysterious and unseen energies. Its celestial cousin, HDP 1b, presents a similar puzzle. This giant planet is another member of the low-density club, bloated to a size that should not be possible for its mass. Here, the mystery may lie in its very composition. Astronomers suspect its atmosphere is rich in water vapor, but the real secret could be the absence of something we consider fundamental, a heavy, rocky core. Unlike Jupiter, which has a dense core of rock and ice at its heart, HDP 1b might lack this central anchor altogether. It could be a nearly uniform sphere of light gases, a world without a solid heart. This raises a profound question. What internal processes or exotic materials are at work, preventing these inflated worlds from simply collapsing under their own immense, yet diffuse gravity? The debate continues as each new discovery about these puffy planets challenges our models of planetary formation and stability. They are cosmic anomalies, reminding us that the universe has more than one way to build a giant. From the bizarrely light to the brutally heavy, we arrive at a world where the very sky weeps metal. WASP 76b is an ultra-hot Jupiter, a gas giant orbiting so perilously close to its star that its dayside is a crucible of incandescent fury. Here, temperatures skyrocket past 4,000 degrees Fahrenheit, hot enough to vaporize iron, turning a foundational element of our world into a shimmering, gaseous mist high in the alien atmosphere. This is not a gentle world of water cycles, but a planet with a weather system born in a stellar forge. The key to its violent meteorology lies in the stark divide between its two faces. The planet is tidally locked, meaning one side is perpetually baked by the star's radiation while the other is cast into eternal, frigid darkness. This creates an unimaginable temperature gradient, a planetary-scale conflict between blistering heat and deep cold. Powerful supersonic winds are born from this chaos, racing from the scorching day side to the freezing night side. These winds carry the vaporized iron across the twilight terminator. As the iron gas crosses into the perpetual night, the temperature plummets by over 1,000 degrees. In the profound chill, the iron vapor can no longer remain a gas. It condenses, coalescing into droplets of molten metal that fall from the sky as a relentless, burning rain. The evidence for this incredible phenomenon comes from the starlight itself. Using sophisticated spectroscopy, astronomers observed the signature or spectral fingerprint of iron vapor at the dividing line between day and night. But as they looked deeper into the night side, that distinct signature vanished. The most logical explanation is that the iron is indeed condensing out of the atmosphere, literally raining out of the sky and disappearing from spectroscopic view. Yet this very process raises more questions than it answers. What unknown chemistry exists in that alien air, allowing for such an efficient and violent precipitation cycle? How can the atmosphere sustain such an extreme temperature difference without stabilizing itself? WASP 76b is more than just a planet. It is a natural laboratory for studying weather patterns we could never conceive of on Earth, a place where the clouds are made of metal and the storms are forged from starlight. Even as metal rains on distant giants, a far more subtle and profound mystery stares back at us from the void. A world so close it orbits the very star next door. Proxima Centauri b circles our nearest stellar neighbor, a red dwarf just over 4 light-years away, placing it squarely within the habitable zone where temperatures could allow for liquid water. But this proximity comes at a strange and dramatic cost. The planet is almost certainly tidally locked, forever presenting one face to its dim, red sun and leaving the other in endless, icy night. This cosmic standstill creates a world that may look like a giant eyeball staring into space. The perpetual dayside, constantly bombarded by stellar energy, could host a single, vast ocean of liquid water, a shimmering blue pupil at the center of this celestial eye. Surrounding this liquid region, a ring of ice might slowly creep towards the terminator line, the boundary between light and dark, while the entire nightside hemisphere remains a single, global glacier of unimaginable depth and cold. The concept of an eyeball planet is a breathtaking possibility, but it is shrouded in immense unknowns. Its actual composition is a complete puzzle. Does it have a solid, rocky surface like Earth, or is it a water world with a global ocean buried beneath a thick shell of ice? Its atmosphere presents another critical question. Red dwarf stars like Proxima Centauri are notoriously volatile, frequently erupting with powerful flares of radiation that could strip away a planet's atmosphere and sterilize its surface. Does this potential eyeball world possess a strong magnetic field, a planetary shield that could deflect these deadly stellar winds and protect any nascent ocean? We simply do not know. Proxima Centauri b is not just another exoplanet. It is a symbol of the ultimate mystery, a potentially habitable world right on our cosmic doorstep whose true nature remains just out of reach, a silent neighbor whose gaze holds secrets we are only beginning to understand. While nearby worlds may hold the potential for life, others have witnessed the entire history of the cosmos. Deep within a dense, ancient swarm of stars known as a globular cluster, a planet named Methuselah endures. It is a staggering 12 billion years old, a relic from a time when the universe itself was in its infancy. This world formed just 1 billion years after the Big Bang, making it older than almost every other star in our galaxy. Its home is a celestial retirement community, a place where ancient stars are packed tightly together in a gravitational dance. The planet itself orbits not one but two stellar corpses, a pulsar and a white dwarf. The pulsar is a rapidly spinning neutron star, the crushed core of a massive sun that died in a supernova explosion long ago. It spins hundreds of times every second, emitting a blistering beam of radiation across space. Its companion is a white dwarf, the faded, Earth-sized ember of another star. This bizarre binary system is all that remains of a cataclysmic stellar drama. The fact that a planet exists here at all is a profound shock to astronomers. The environment inside a globular cluster is one of extreme chaos, with stars constantly passing near one another, their gravitational pulls capable of tearing young planetary systems apart. For Methuselah to have survived, it must have either formed in an impossibly stable pocket, or it was a wandering planet captured by this binary system after its own parent star perished. Its composition is a direct window into the early universe. If it is a gas giant, it is a cosmic survivor that weathered the violent death of its original star and the gravitational turmoil of the cluster. But it might also be something far stranger, a world with a core made of primordial elements forged in the first generations of stars. These would be elements far simpler and older than the heavy metals that make up our own Earth. Methuselah is more than just an old planet. It is a living fossil, a piece of cosmic archaeology that challenges every model we have for how and where planets can form. Its very existence proves that worlds were being built in the most chaotic and unlikely places, even before our own sun was a flicker in the darkness. The existence of a planet older than our galaxy shows the sheer resilience of worlds, but others are forged in a crucible of immediate and violent extremes. Orbiting impossibly close to their parent stars are the ultra-short period planets, worlds where a single year is measured in mere hours. Kepler 10b, Kepler 78b, and Korot 7b are among the most extreme examples, rocky spheres so scorched by stellar radiation that their surfaces are almost certainly global oceans of incandescent lava. These are not gas giants with hidden layers, but terrestrial planets caught in a permanent state of infernal melting. The fundamental question about these worlds is a matter of their very origin. Are we looking at the naked, blazing cores of former gas giants, planets whose thick atmospheres were boiled away by the relentless stellar wind? Or are they super-dense, iron-rich worlds that somehow migrated inward to this hellish orbit, their surfaces now a churning cauldron of molten rock and metal? Each possibility paints a dramatically different picture of their history and their internal composition. Their surfaces are so hot that they are actively evaporating. Just as water turns to steam on our world, the very rock on these planets is vaporizing, creating a thin, tenuous atmosphere not of gas but of vaporized minerals. Imagine a sky filled with clouds of silicate and sodium, a haze of vaporized rock that condenses only to fall back into the global lava sea as a rain of tiny, molten pebbles. This is a weather cycle completely alien to our solar system, a place where the very ground you stand on would boil away into the sky. These lava worlds push the concept of a planet to its absolute limit, challenging us to understand how a rocky body can survive in such an unforgiving environment and what secrets its vaporized crust might hold about the final frontiers of planetary existence. The churning lava oceans of ultra-short period planets show us worlds defined by fire, but the cosmos holds another, more fluid extreme. GJ 1214b presents a mystery wrapped in a deep global shroud. This sub-Neptune world is larger than our own Earth but smaller than the ice giants in our solar system, and it may be almost entirely composed of water. Data from the Hubble Space Telescope revealed its secret during a transit as the planet passed in front of its star. Instead of showing the distinct chemical fingerprints of common gases like hydrogen or methane, the starlight filtering through its atmosphere was completely flat. This featureless transmission spectrum tells us that something is blocking our view, preventing us from seeing deep into the atmospheric layers. One compelling explanation is a thick, high-altitude haze, a global smog of complex chemicals that obscures everything beneath it. But the more tantalizing possibility is a global ocean. Not an ocean like the ones on Earth, but a planet-wide body of water so deep and vast it defies easy comprehension. The immense pressure from the overlying atmosphere could be creating an ocean in a supercritical state. This is a strange phase of matter where the distinction between liquid and gas blurs into a single, hot, dense fluid. Imagine a world where the very ocean is a churning, seething fluid that behaves unlike any water we know. Alternatively, the planet's structure could be layered like a cosmic onion. It might possess a solid, rocky core surrounded by an unimaginably deep ocean of water, all enclosed within a thick, hydrogen-rich atmosphere. This would make it a true water world, a place where the very concept of land does not exist. Yet there is another, even stranger potential hidden in the crushing pressures of its interior. Deeper than any hypothetical ocean, the pressure could be so intense that water molecules are forced into exotic, solid forms known as hot ices. These are not the familiar icy crystals from your freezer, but high-pressure phases of water where the molecules lock into a crystalline structure even at scorching temperatures. This would mean a solid core of hot ice, a paradoxical substance that is both frozen and incredibly hot, forming the heart of a world that is fundamentally alien. GJ 1214b forces us to question what we mean by a water world. Is it a steamy, shrouded globe with a perpetual, supercritical sea, or is it a world with a heart of burning ice? Its silent, flat spectrum holds the answer, a secret kept by a planet that may be more ocean than rock. While water worlds and molten spheres test our ideas of habitability, other planets exist in a state of constant celestial ballet. Kepler 16b is a world with two suns, a real-life counterpart to the fictional Tatooine. This Saturn-sized gas giant orbits a pair of stars that are themselves locked in a tight gravitational dance, a smaller, cooler red dwarf and a larger, sun-like star. From the planet's surface, you would witness a spectacular and ever-changing sky with double sunsets and double sunrises, where the two stars sometimes eclipse each other, casting complex, shifting shadows across the landscape. The very existence of such a world was once considered a fantasy by astronomers. The chaotic gravitational environment of a binary star system was thought to be too violent and disruptive for the slow, gentle process of planet formation to ever succeed. The discovery of Kepler-16b shattered that assumption, proving that planets can form in the most tumultuous of stellar neighborhoods. But this beautiful duality comes with profound physical challenges. The planet experiences a constant gravitational tug-of-war from its two parent stars. This relentless pull does not just affect its orbit, it likely churns the planet's interior, generating immense tidal friction and internal heat. This extra energy could be inflating the planet, puffing up its atmosphere to a size larger than expected for a world of its mass, much like the puffy giants we encountered earlier. The stability of its atmosphere is also thrown into question. The combined and varying stellar radiation from two different stars, each with its own output and flare activity, would create a climate of wild extremes. A planet might experience intense heating pulses as one star passes in front of the other, or prolonged periods of reduced light. This could drive powerful, unpredictable weather patterns, with supersonic winds constantly attempting to balance the uneven heating across the globe. Perhaps the most intriguing mystery lies in its very composition. Could the dust and gas that coalesce to form this planet have been enriched with unique materials, compounds that only crystallize or form under the specific pressure and temperature gradients found in a binary protoplanetary disk? The dust grains that built Kepler-16b were subjected to a more complex environment than those around a single star, potentially creating a world with a chemical fingerprint unlike any other. Kepler-16b is more than a scientific curiosity. It is a testament to the universe's relentless creativity, building worlds in places we once believed were barren, and challenging us to expand our definition of where planets can call home. From the cosmic ballet of binary suns, we find a world that seems to dissolve into a wisp of cloud. Kepler-51b is a celestial confection so light and airy it defies the very concept of a solid world. Its density is among the lowest ever measured, making Saturn seem like a dense ball of rock by comparison. This planet is a true cotton candy world, a puffy giant with a composition that remains one of astronomy's most delightful puzzles. How can a planet of such size possess so little substance? One compelling theory points to a dramatic and fleeting existence. The planet is incredibly young, a cosmic toddler in planetary terms. It may be composed of the lightest elements, hydrogen and helium, but its proximity to its star is causing a catastrophe in slow motion. The intense stellar radiation could be heating its upper atmosphere to a fever pitch, causing it to billow out and escape into space like steam from a boiling kettle. We might be witnessing this world in the middle of a dramatic transformation, losing its atmosphere at a staggering rate as it evolves before our eyes. Another possibility delves into the exotic. The planet's incredible fluffiness might not come from gas alone, but from vast quantities of light, fluffy ices. Imagine ices not of frozen water, but of methane or ammonia, mixed with thick hydrocarbon hazes similar to those found on Saturn's moon Titan. These materials could form a deep, bloated envelope around a much smaller core, creating a planet with the consistency of a spun sugar cloud. This youth is the key to the mystery. Kepler-51b is not a stable, ancient world. It is likely a snapshot, a brief and volatile stage in the life of a gas giant that we are fortunate enough to catch in the act. Most planets pass through this puffy phase quickly before they cool and contract into the more familiar giants we know. To find one at this exact moment is like stumbling upon a butterfly just as it emerges from its chrysalis. It offers a rare, living portrait of planetary evolution, a glimpse into a transitory chapter that most worlds leave behind in their infancy. This cosmic cotton candy challenges us to understand not just what a planet is, but what it is in the process of becoming. The heat of a lava world pales before the stellar fury unleashed upon Kelt 9b. This is a planet with a dayside temperature soaring above 7,800 degrees Fahrenheit, a searing heat that surpasses the surface of some red dwarf stars. It orbits so close to its blue, Type-A host star that a full year is a blistering day and a half long. The star itself does not just shine upon this world, it actively consumes it. A relentless torrent of high-energy radiation is boiling the planet's atmosphere away, creating a magnificent comet-like tail of lost gases that stretches for millions of miles into the void. We are witnessing a planetary evaporation in real time. Spectroscopy has confirmed that the escaping atmosphere is no ordinary mix of gases. It is a vaporized brew of heavy metals containing iron and even titanium, elements that would be locked in rock on a cooler world. Here they exist as free-floating atoms in the scorching air. This discovery alone is staggering, but it points to a deeper, more fundamental mystery. What lies at the heart of this evaporating giant? The intense heat and violent stellar winds have stripped away the outer layers, offering us an unprecedented, if terrifying, look into a planet's interior. Is Kelt 9b the exposed, dying core of a once mighty gas giant, a Jupiter-like world that migrated too close to its sun and is now being skinned alive? Or is it something even more extreme, a colossal rocky super-Earth, a planet with several times the mass of our own world that is being blasted down to its bare metallic skeleton? The vaporized metals we detect could be the very bedrock of this world, boiling directly into space. On Kelt 9b, the rules of chemistry as we know them simply do not apply. Molecules cannot form in such an energetic soup of atoms. The conditions are so extreme that they mimic the environment inside a star, forcing matter into states we can barely replicate in our most advanced laboratories. This world is not just an astronomical object, it is a natural particle accelerator, a cosmic furnace that is dismantling a planet atom by atom and challenging our most basic assumptions about the boundary between a world and its star. The blistering heat of Kelt 9b fades into a different kind of cosmic spectacle, one not of evaporation but of colossal architecture. Far beyond our solar system lies the J1407b system, a place that may host the most expansive set of rings ever imagined. The central object is likely a brown dwarf, a failed star too small to ignite sustained nuclear fusion, but the true marvel orbits this dim substellar body. Something out there, perhaps a young, giant planet, is surrounded by a ring system of such staggering proportions that it dwarfs our entire solar system's planetary decorations. These proposed rings stretch over a distance nearly 200 times greater than the magnificent rings of Saturn. To grasp that scale, if Saturn's rings were replaced with this colossal structure, they would dominate our night sky, appearing larger than a full moon and revealing intricate bands and gaps visible to the naked eye. The composition of these rings is a matter of intense debate. Are they made of pristine, reflective ice like the rings of Saturn but on a galactic scale? Or are they darker, composed of countless trillions of rock and dust particles, absorbing the faint light from the brown dwarf? The most compelling clue comes from the ring's structure itself. Observations show complex patterns of gaps within the proposed disk, clear signatures of gravitational clearing. This is exactly what astronomers see in the protoplanetary disks around young stars, where newborn planets sweep their orbits clean of dust and gas. This suggests we are not looking at a stable, permanent ring system like Saturn's, but at a cosmic maternity ward. We may be witnessing a moon-forming disk in real time, a vast reservoir of material from which entire families of exomoons are currently coalescing. The sheer mass of this structure is incredible, potentially containing enough material to form several worlds the size of Earth or Mars. The true nature of the object at the center remains one of astronomy's great puzzles. Is it a superplanet, a colossal world still in its fiery youth, actively building its own lunar system? Or is it something else entirely, a strange celestial object caught in a brief, luminous chapter of its evolution? The J1407b system offers a fleeting glimpse into a process we have never directly seen, the birth of moons around a distant giant, a dramatic performance on a stage of almost impossible size. Deep within the constellation of Coma Berenices, a star system hums with a perfect, almost musical harmony. Astronomers recently discovered that 6 worlds orbit the star HD1 10067 in a precise gravitational symphony, a rare configuration known as orbital resonance. For every 6 orbits the innermost planet completes, the next one completes 5, and the next one 4, and so on, like a perfectly tuned cosmic clockwork. This resonant chain has remained unbroken for billions of years, suggesting a history of profound peace, free from the violent collisions and gravitational upheavals that scrambled our own solar system. Yet 2 of these worlds, planets 16 and 17 in our journey, are enigmas wrapped in this serene dance. They are sub-Neptunes, larger than Earth but smaller than the ice giants Uranus and Neptune. Their size places them in a puzzling category. They are too massive to be simple, solid rock like our own planet, but they are not large enough to have gathered the immense hydrogen envelopes of a true gas giant. So what are they made of? One compelling possibility is that they possess a solid, rocky core, much like Earth, but this core is utterly engulfed by a deep, thick atmosphere of hydrogen and helium, a shroud of primordial gas left over from the system's birth. This atmosphere would not be thin and breathable like our own. The pressure from its immense weight would crush anything that ventured too deep, creating conditions where gases behave like strange, super-dense fluids. Another, even more intriguing theory suggests these are water worlds of an unimaginable scale. Their rocky hearts could be surrounded by a global ocean so deep that it defies earthly comparison. But this would be no ordinary sea. The pressure at such depths would be millions of times greater than at the bottom of our Mariana Trench, forcing the water into exotic high-pressure states. It could form a mantle of supercritical water, a fluid that is neither liquid nor gas, or even layers of hot, solid ice. These are not the familiar ice crystals from your freezer, but high-pressure phases where water molecules lock into crystalline structures even at temperatures of hundreds of degrees. This would create a paradoxical world with a scorching hot, solid ice core. The resonant harmony of their orbits tells a story of a calm and orderly upbringing, but it reveals nothing of the chaotic, alien conditions that likely rage beneath their clouds or within their abyssal oceans. They are a beautiful contradiction, worlds of serene celestial motion that may hide interiors of unimaginable pressure and exotic chemistry. The serene orbital harmony of one system gives way to profound gravitational discord in another. Far beyond the resonant worlds, astronomers discovered a gas giant named HD 131399 AB in a complex triple star system, a world whose very existence seemed to defy stable orbits. Yet its story connects to a deeper and more pervasive cosmic mystery, the ghostly influence of dark matter. Across the galaxy, some star systems exhibit strange gravitational tugs, subtle wobbles that cannot be explained by the visible planets and stars alone. These anomalies once led to a fringe but fascinating theory, the idea of dark matter planets. Imagine a world built not from atoms, but from the invisible substance that makes up most of the universe's mass. Such a planet would not reflect, absorb, or emit any form of light. It would be completely transparent and undetectable to our telescopes, revealing its presence only by the gentle pull of its gravity on neighboring stars. You could pass a beam of light directly through it and see nothing at all. While this idea is no longer considered a likely explanation for most gravitational puzzles, it represents the ultimate frontier of the unknown. A dark matter world would be a cosmic phantom, a sphere of material that interacts with our familiar reality through gravity alone. Its composition would be a total enigma, a substance that passes through ordinary matter like a ghost through a wall. This wild theory reminds us that when we encounter a true anomaly, our first step is often to explore the most extraordinary possibilities. We test the limits of our imagination before the data guides us toward a more mundane, yet still incredible truth. The case of dark matter planets shows how the search for strange new worlds constantly pushes us to question the very nature of matter itself, and to wonder what truly invisible wonders might be hiding in the dark. The planet WASP 12b is being devoured by its star, but its true strangeness lies in what it is made of. This world possesses one of the highest carbon to oxygen ratios ever measured, a chemical signature that points to a reality far stranger than simple rock and metal. Imagine a world where the fundamental geology is based not on silicon and oxygen, the building blocks of Earth's crust, but on carbon. Deep within its interior, under pressures that crush matter into new forms, the carbon is likely undergoing a radical transformation. Scientists theorize that much of the planet's interior could be a solid layer of diamond, a crystalline lattice thousands of miles thick, but the extreme conditions might be forging something even more exotic. There is the speculative possibility of a substance known as superdiamond, a form of carbon that is even harder and more densely packed than the gemstone we know, or perhaps long, stable chains of carbon atoms forming a matrix of unimaginable strength. This is a world with a heart of celestial crystal, yet the alien chemistry does not stop deep underground. Its atmosphere is a toxic, hazy brew. The intense heat from the nearby star, combined with the abundance of carbon, could be creating a sky filled with complex hydrocarbons. Instead of water vapor and nitrogen, the air might be thick with a global smog of compounds resembling tar and soot. This would create a perpetual, high-altitude haze that absorbs light, contributing to the planet's already dark and bloated appearance as its outer layers are stripped away. So while we watch this world slowly die, pulled apart by its star's gravity, we are also looking at a cosmic alchemist's masterpiece. It is a planet with a diamond heart, breathing an atmosphere of primordial sludge, a stunning paradox of immense value and profound toxicity existing in the same dying world. Drifting alone through the cold, starless void between galaxies, rogue planets are the ultimate cosmic loners. These are worlds untethered from any sun, cast adrift by gravitational chaos to wander the infinite dark. One such candidate, CFBD Sir 214900403, offers a chilling glimpse into this nomadic existence. Without a star to warm it, this planet is a frozen relic, its surface temperature plummeting to hundreds of degrees below zero. The fundamental question about its composition is a puzzle of ice and gas. Is it a super-Earth, a colossal frozen rock with a surface of solid ice as hard as steel? Or is it a failed gas giant, a shrunken and contracted sphere of hydrogen and helium that never grew to full size? In such profound cold, its very atmosphere could be collapsing. We are familiar with snow made of water, but on a world this frigid, different gases freeze directly out of the air. The surface could be covered in a blanket of snow made of nitrogen, the same gas that makes up most of our own air. Or it could be a frost of carbon dioxide, what we know as dry ice, creating a crunchy, frozen crust over an even more alien landscape. These worlds are so dark and distant that they are nearly invisible to our telescopes. We only detect the closest and largest ones through a subtle trick of gravity, a phenomenon called microlensing, where the planet's gravity briefly acts as a lens, magnifying the light of a faraway star behind it. This fleeting signal reveals the planet's presence, but almost nothing about its character. The composition of a rogue planet remains one of astronomy's greatest unknowns. Is it a frozen wasteland of exotic ices, or a dense, cold ball of gas, silently tracing an eternal path through the endless night? The surface of Co-Rho T7b is a churning global inferno, but the true mystery lies deep beneath its oceans of lava. What kind of heart beats within this scorched world? The intense gravitational pull from its star doesn't just lock the planet in place, it constantly kneads its interior like cosmic dough. This tidal flexing generates immense friction and heat, likely creating a core that is entirely molten, a vast, swirling sphere of liquid iron and nickel. On Earth, our solid inner core spinning within a liquid outer core generates a protective magnetic field. Here, the entire core may be liquid, a single, seething dynamo. Could this homogeneous molten sphere still generate a magnetic field? The physics becomes strange under such extreme conditions. The sheer heat and turbulent motion of the liquid metal might be enough to create a weak global magnetic field, a fragile shield battling the relentless stellar wind. Without it, the planet's vaporizing atmosphere would be stripped away even faster. This leads to another startling possibility. The surface of the lava ocean might not be entirely uniform. As vaporized rock rises from the hottest regions, it could cool and condense in the slightly less hellish pockets of the planet's terminator line, the fragile border between day and night. There, minerals with a higher melting point might solidify into thick, viscous slags. These could coalesce into vast, floating islands, continents of solidified mineral drifting slowly across the incandescent sea. They would be temporary and unstable, constantly remelting on the day side and reforming on the night side, in a slow, perpetual dance of creation and destruction. This would be a geology in its most primal state, a world with a crust that is born and dies within hours, a stark contrast to the stable continents of Earth. Co-Rho T7b presents a vision of a planet stripped down to its most violent and essential processes, where the very concepts of land and core are redefined by fire and gravity. The blistering fate of a gas giant stripped to its skeleton offers a different kind of revelation. We now confront the hypothetical Chthonian planet, a ghost of a world born from stellar violence. This theoretical class of celestial body begins its life as a majestic gas giant, a Jupiter-like world with a vast, swirling atmosphere. But if it migrates too close to its parent star, a catastrophe unfolds. The relentless stellar winds and intense radiation begin to scour the planet clean, blasting its gaseous envelope away into the void. This process continues until the entire atmosphere is completely stripped away, leaving behind only the planet's central core, a naked and exposed sphere. This remnant would be nothing like the terrestrial planets in our own solar system. It would be the colossal, dense heart of a giant, a ball of rock and metal that once lay buried under thousands of miles of hydrogen and helium. What would the composition of such a core be? Under the immense pressures that existed deep within the original gas giant, the core's materials would have been transformed. It could be a massive sphere of solid iron, or a mix of silicates and metals compressed to an almost unimaginable density. The intense pressure might have even crushed carbon into a thick layer of diamond, creating a world that is literally a planetary core made of gemstone. The staggering possibility is that we may have already discovered these exposed cores without even realizing it. Some of the ultra-short period planets we've detected, those incredibly dense, rocky worlds orbiting perilously close to their stars, could in fact be Chthonian planets. We see a small, hot, super-dense world and assume it is a rocky super-Earth, but it might be something far more dramatic, the stripped-down carcass of a gas giant. How could we tell the difference? A true Chthonian core would be significantly larger and more massive than a planet that formed as a simple ball of rock. Its density would be extraordinarily high, and its composition might show chemical signatures of its violent past, perhaps an abundance of heavy elements that were once sequestered deep within a giant's interior. The search for these phantom cores forces us to look at the known exoplanets in a new light, wondering if the most extreme worlds we have catalogued are not the beginning of a planetary story, but its dramatic, fiery end. 40 light-years away, a single, faint red dwarf star is home to a treasure trove of Earth-sized worlds. The TRAPPIST-1 system contains 7 known planets, but 3 in particular captivate astronomers and dreamers alike. Worlds E, F, and G all orbit within the star's habitable zone, that temperate region where liquid water could theoretically exist on a planet's surface. Yet this shared orbital real estate does not guarantee similar fates. Each of these 3 siblings appears to be a completely different kind of world, their compositions a trio of profound mysteries. The innermost of the 3, TRAPPIST-1e, is a world of tantalizing potential. Its size and density suggest it could be a rocky planet much like our own, but with a crucial and dramatic difference. The data indicates a density slightly lower than Earth's, a small but critical clue. This has led to the compelling theory that TRAPPIST-1e could be a water world, a planet completely engulfed by a single global ocean hundreds of miles deep. There would be no continents breaking its surface, no mountain ranges reaching for the sky, just an endless expanse of water under a red sun. The pressure at the bottom of such an ocean would be crushing, creating layers of exotic, hot ice that form a strange, solid floor above the rocky core. This is a world that is landless, a vast aquatic globe where life, if it exists, would be forever confined to the waters. Moving outward, we encounter TRAPPIST-1f. This planet's density is even lower, pointing to a composition rich in volatile materials. One possibility is that it is shrouded in a thick, dense atmosphere, a global blanket of unknown gases. This could be a Venus-like world, but with a chemistry we can scarcely imagine, its surface hidden beneath perpetual, opaque clouds that trap heat and create a crushing, infernal pressure. Yet there is another, more hopeful scenario. That low density could also be explained by a thick, insulating shell of water ice. If TRAPPIST-1f possesses a surface of ice, the gentle tidal heating from its star and sibling planets could be enough to maintain a vast, dark ocean of liquid water trapped between the frozen crust and a rocky seafloor. This would make it a cosmic cousin to moons like Europa or Enceladus, a frozen snowball hiding a secret, subglacial sea with the potential for life entirely separate from the sun's energy. The outermost of this habitable zone trio, TRAPPIST-1g, is the largest of the 7 planets, and its composition is perhaps the most bizarre. Its density measurements do not neatly match any single substance we know. It seems to be an awkward hybrid, a world built from a non-Earth-like mixture of rock and light volatiles. It might possess a rocky core, but one that is swaddled in a deep, global layer of water in various exotic forms, or a strange, puffy atmosphere of hydrogen and helium that it somehow managed to retain despite the star's activity. The sheer variety is what makes this system a comparative planetologist's dream and nightmare. Here, around one small star, we have a perfect laboratory to study how planets with similar origins can evolve into such radically different end states. Why is one world potentially an ocean, another an ice ball, and a third a strange hybrid? The data we have so far, rather than providing answers, only deepens the intrigue, reminding us that being in the right place for life is only the first step in a planet's long and complex story. GJ 436b presents a paradox wrapped in a cosmic breeze. This Neptune-sized world orbits so close to its star that its surface temperature is a scorching 800 degrees Fahrenheit, far too hot for common planetary molecules to hold their form. Yet when astronomers looked, they found the distinct spectral signature of methane, a gas that should be ripped apart by the intense stellar radiation. It is like finding a perfect snowball sitting in the heart of a blast furnace. The explanation for this bizarre contradiction may lie in what is happening to the planet itself. Observations show a vast, comet-like tail of hydrogen gas streaming away from the world, a clear sign that its atmosphere is being actively blasted into space by its star. This constant evaporation is creating a planetary wind, a stream of lost gas stretching for millions of miles. we are not looking at a stable world, but one in the process of being unmade. As the outer layers of its atmosphere are stripped away, deeper, previously hidden layers are being exposed to our telescopes. The methane we detect might not be sitting in the upper atmosphere as we would expect. Instead, it could be a temporary product, constantly forming in these newly revealed, cooler lower layers, only to be destroyed as it rises into the stellar inferno above. This creates a strange chemical cycle that maintains a wisp of methane against all odds. But the true mystery of GJ436b might be even more alien. Some scientists theorize it could be a steam world. Any water present on this scorching globe would be subjected to a relentless barrage of ultraviolet radiation from the star. This intense energy could be tearing the water molecules apart, dissociating them into a swirling soup of hydrogen and oxygen. The hydrogen escapes, feeding the planet's vast tail, while the oxygen might be left behind to engage in bizarre chemical reactions we are only beginning to model. What does an atmosphere dominated by atomic oxygen and other radical elements look like? How does it behave? This is a type of atmospheric chemistry we have never seen before, a ghostly, energetic shroud born from the dissection of water itself. GJ436b is not just a planet losing its air, it is a laboratory where the fundamental rules of atmospheric science are being rewritten in real time. The solar system's own moon Io shows us just how powerful gravity can be as a planetary forge. This volcanic world is relentlessly squeezed and stretched by the gravitational pull of Jupiter and its sister moons, creating so much internal friction that its interior is a perpetual inferno. Now imagine that same ferocious process unleashed not on a moon, but on a full-sized planet orbiting a distant star. A rocky world caught in a tight, eccentric dance around a massive gas giant would experience this tidal heating on a colossal scale. Its orbit would not be a perfect circle, but a stretched-out ellipse, ensuring that the gravitational pull from its giant parent changes dramatically with every pass. The planet would be constantly flexed, its very crust and mantle needed by these immense, shifting forces. The resulting internal heat could be far greater than that generated by radioactive decay inside Earth. This would create a world of unimaginable volcanic fury, a place where the surface is continuously repaved by rivers of incandescent lava and blanketed in thick global layers of volcanic ash. Such a planet would be a geological chameleon. Any attempt to determine its true, underlying composition from a distance would be foiled by its own hyperactivity. We might measure the density of the material on its surface, but that would only tell us about the freshly erupted lava, not the ancient primordial rock hidden deep below. Is this world a carbon-rich body with a heart of diamond or an iron-poor sphere of lightweight rock? Its volcanic shroud would keep that fundamental secret, presenting only its youngest, most temporary face to the cosmos. This constant renewal would also erase its history. Impact craters would be filled in almost as soon as they form, and any evidence of past oceans or ancient continents would be swallowed by the magma. The planet would live in a permanent, fiery present, its true nature and its entire story locked away beneath a surface that never stops moving. Even a world losing its atmosphere is not the final word on cosmic extremes. Orbital data from the red dwarf star Gliese 436 hinted at a second world, a gravitational whisper we call Gliese 436c. This planet remains unconfirmed, a hypothetical body proposed to explain a subtle wobble in its star's motion. Yet its very possibility opens a door to a realm of physics that defies earthly experience. If it exists and possesses the mass to create such a noticeable tug, it could be a world of immense density, a place where pressure is the defining force of reality. Within such a planet, matter would be forced into states that are impossible to create in any laboratory on Earth. Deep in its interior, the crushing weight could transform simple hydrogen, the lightest element, into a shimmering liquid metal. This metallic hydrogen would flow like a bizarre, silvery ocean, a superconductor capable of generating magnetic fields of unimaginable power. Water, a substance we know as solid, liquid, or gas, would undergo an even stranger transformation. It could become superionic water, a paradoxical phase that is both a solid and a liquid at the same time. In this state, the oxygen atoms are locked into a rigid crystalline lattice, like the structure of ice, but the hydrogen nuclei flow freely through this solid cage like a liquid metal. This is not water as we know it. It is a conductive ice, a material that can carry electric current while remaining a solid. A world hosting such exotic matter would be a place where the very definitions of our physical world begin to blur. What does the surface of such a planet look like? Could there be continents of supersonic ice glowing from internal heat under a sky of liquid metallic hydrogen? The hypothetical nature of Gliese 436c does not diminish its power. It represents the ultimate frontier of planetary science, a concept that challenges us to wonder what forms matter can take when pushed to its absolute limits by the sheer, silent force of gravity. The Kepler-36 system presents a paradox of cosmic neighbors. Two worlds, Kepler-36b and c, orbit the same star in an astonishingly tight embrace. Their paths are so close that the distance between them is a mere 1.2 million miles, just 5 times the span from the Earth to the Moon. From the surface of one planet, the other would appear as a colossal, swirling sphere dominating the sky, several times larger than our full moon. Yet this breathtaking proximity hides a fundamental and inexplicable difference. Despite forming in the same stellar nursery, these two siblings are made of entirely different stuff. Kepler-36b is a super-Earth, a dense, rocky world with a mass over 4 times that of our own planet. Its composition is likely iron and rock, a solid sphere forged in fire. Its neighbor, Kepler-36c, is a mini-Neptune. It is slightly larger in size but possesses less than half the density, meaning it is a puffy world enveloped in a thick, gaseous shroud of hydrogen and helium. This is the core of the mystery. How can two planets that formed right next to each other from the same reservoir of dust and gas end up so radically different? It is like finding a solid ball of iron orbiting next to a giant, fluffy cotton candy cloud, with both objects emerging from the same cosmic kitchen. Their stark contrast forces a complete rethinking of planetary formation. The classic model suggests that planets coalesce in an orderly fashion from a protoplanetary disk, with rocky worlds forming close to the star and gas giants forming farther out. But here, a rocky world and a gaseous world are practically touching. This bizarre arrangement points to a violent and dynamic history of planetary migration. Perhaps the mini-Neptune, Kepler-36c, formed in the cooler outer regions of the system, where it could easily accumulate its vast gaseous envelope. Then some gravitational disturbance, a push from another planet or a tug from the disk itself, sent it spiraling inward to its current orbit, parking it improbably next to the rocky super-Earth that was forming all along. Another possibility is even more chaotic. Maybe both planets started as similar rocky cores, but only one was fortunate enough to quickly grab and hold onto a massive atmosphere from the primordial disk before the young star's radiation blew the rest of the light gases away. The other core, left behind, remained a barren rock. Their current, resonant orbits, which keep them locked in a stable gravitational dance despite their closeness, suggest they have maintained this strange partnership for billions of years. This celestial odd couple is a living fossil of planetary migration, a permanent monument to the turbulence of a young solar system, and a direct challenge to our understanding of how worlds are built. This hot Saturn hides a secret that defies our understanding of how gas giants are built. While planets like Jupiter are vast spheres of hydrogen and helium with relatively small rocky hearts, HD 149026b is different. Its identity is dominated by a mysterious, oversized core, a heart of unimaginable density that makes up a staggering portion of the entire planet. This world is not a lightweight gas bag, but a cosmic anomaly whose immense gravity tells a story of extreme formation. The core of this planet is estimated to be between 70 and 90 times the mass of our entire Earth. To grasp that scale, picture compressing every mountain, every ocean, and every continent of our world, then repeating that process 70 times over and crushing all that material into a single, colossal sphere buried at the center of a Saturn-sized world. That is the hidden engine of HD 149026b. The sheer mass of this core raises a fundamental question about its composition. Is it a giant ball of rock and ice, a testament to an incredible abundance of heavy elements in its birth cloud? Or has the pressure from all that weight crushed the material into something even more exotic, a state known as degenerate matter? This is a form of matter so densely packed that the rules of everyday physics break down, and the substance behaves more like a single, giant atom than a collection of rocks. Such a core would be incredibly hot and dense, a remnant of the violent forces that forged it. The formation of this planetary paradox is a puzzle. Did it begin as a super-sized rocky planet that later gathered a modest coat of gas, never growing to full Jupiter proportions? Or was it a standard gas giant that experienced a catastrophic collision, a planetary crash of such violence that its outer layers were stripped away, leaving its massive heart exposed? The existence of this burned-out core suggests its entire star system was once rich with heavy metals, the cosmic building blocks for rock and ice. It is a world that tells us planetary construction can follow a blueprint we have never seen in our own solar system, creating giants with hearts of stone and secrets of impossible density. Floating like a solitary pink blossom in the void, GJ504b is a world captured by our telescopes not just as a data point, but as a direct, hauntingly beautiful image. This young gas giant, glowing with the residual heat of its formation, presents a pastel sky that defies the typical orange and tan of our own Jupiter. Its delicate pink hue is a direct clue to its atmospheric composition, a clue that has only deepened the mystery. For a planet of its estimated temperature, the laws of atmospheric chemistry we understand predict a sky rich with methane. Yet the spectrum of light from this pink world tells a very different story. The distinct fingerprint of methane is conspicuously, bafflingly absent. It is as if we found a forest with no trees, an ocean with no water. The very chemical we expect to see defining its atmosphere has simply vanished. So what unknown process is scrubbing the methane from this world's air? One compelling theory involves a dramatic planet-wide churn. Imagine an atmosphere so violently mixed that powerful, vertical winds are constantly dragging gases from the upper layers down to the crushing depths below. In this scenario, carbon monoxide, which is present in the atmosphere, is pulled down to regions of immense pressure and heat before it can ever react with hydrogen to form methane. The planet's own internal turbulence could be preventing the methane from ever appearing, like a chef constantly removing ingredients from a recipe before they can be combined. The result is an atmosphere paradoxically rich in carbon monoxide and poor in methane, a chemical state that should not exist for long in such a world. Another possibility points to an exotic atmospheric ingredient we have not yet identified. Perhaps the pink glow itself is a signature of this mystery compound. The planet's air might be filled with a thick, high-altitude haze of complex hydrocarbons, a global smog that selectively absorbs certain colors of light, giving the world its rosy tint and simultaneously masking the methane signal from our view. Or perhaps some unknown catalyst in the atmosphere is actively and efficiently breaking methane molecules apart as fast as they form, a continuous, invisible chemical demolition that leaves no trace. GJ504b is a stark reminder that our models of planetary science, built from the limited examples in our own solar system, are merely a first draft. This serene pink giant is quietly conducting an experiment in atmospheric chemistry we are only beginning to decode, its pastel beauty hiding a turbulent and secret heart. Beneath a hypothetical world's churning ocean lies a form of ice that burns the hand even as it refuses to melt. This planet, many times more massive than Earth, is a true water world, its entire surface a single, unbroken sea hundreds of miles deep. There are no shorelines, no continents, just an endless abyss of liquid water under a thick, steamy atmosphere. But as you descend into the crushing darkness, the familiar rules of physics begin to warp. The immense pressure from the colossal weight of water above transforms the ocean floor into something utterly alien. Long before you could ever reach the rocky core, the water itself turns solid. This is not the delicate, frozen crystal of a snowflake. This is exotic ice, a form of water so densely compressed that it remains solid even at temperatures of hundreds of degrees. At these profound depths, the pressure forces water molecules into tight, orderly crystals known as Ice 6 and Ice 7. These are hot ices, paradoxical substances that are simultaneously scorching to the touch and solid as rock. They form a mantle of crystalline water that could be thousands of miles thick, a geological layer that acts as the planet's true crust, separating the liquid ocean above from the silicate and metal core below. The boundary between the liquid sea and this solid ice mantle would be a bizarre and dynamic frontier. It would not be a sharp, clean line like the surface of a frozen lake. Instead, it would be a vast, slushy, and turbulent transition zone, a realm of constant change. Here, the intense heat from the planet's core below battles the crushing pressure from the ocean above, creating a chemical environment we can scarcely model. Minerals from the rocky core might dissolve into this slushy layer, creating brines of unknown composition. Strange chemical reactions could be occurring in this perpetual, semi-solid state, reactions that have no parallel on Earth. Could complex probiotic chemistry arise in this churning, pressurized limbo between liquid and hot solid? The entire planetary structure is an inverted version of our own world. Instead of a rocky crust with patches of ocean, this world has a liquid surface with a bedrock of hot ice. Its geology is defined not by tectonic plates, but by the slow, convective churn of its ice mantle and the hidden heat from its core. This is a world where the very ground beneath the waves is a burning, crystalline fortress, a secret landscape hidden forever from the light of any sun. The silent cinders of a dead star hold a secret that rewrote our cosmic history. Orbiting the pulsar known as PSRB 1002, 12 are the very first planets ever discovered beyond our solar system, a trio of worlds born from absolute destruction. Their existence is a profound paradox. A pulsar is the rapidly spinning, hyper-dense corpse of a massive star that died in a cataclysmic supernova explosion, a blast so violent it should have annihilated any planetary system that once existed. So how did these worlds survive? The answer lies in their terrifying origin story. They are not survivors but phoenixes. One possibility is that these are the scorched skeletal remains of former gas giants. The original star's death would have blasted away their vast gaseous atmospheres, leaving behind only their charred metallic cores now orbiting the stellar ghost. The other, even more dramatic theory is that they are second-generation planets. After the supernova, a vast cloud of rich, heavy element debris would have expanded outward. Within this cloud of stellar ashes, a new disk of dust and gas could have coalesced, a disk forged from the remains of the dead star itself. From this cosmic graveyard, entirely new worlds were born. This second genesis would create planets unlike any other. Their composition would be a direct sample of a supernova's forge, heavily enriched with the heaviest elements. Imagine a world with a crust laced with gold, a mantle threaded with uranium, and a core of solid platinum. These could be the most metal-rich worlds in the entire galaxy, not in the musical sense, but in a literal, geological sense. They are cosmic alchemy made manifest, celestial bodies built from the rarest elements the universe can produce. Yet this incredible wealth comes at a price. These planets are bathed in the pulsar's relentless death beam, a constant barrage of high-energy radiation that sterilizes their surfaces. They are treasures of unimaginable value orbiting a beacon of perpetual death, a stark reminder that the universe creates its greatest wonders in the most hostile of environments. The ultimate transformation of a gas giant leaves behind a world of ethereal simplicity. Imagine a planet that has lost everything but its lightest gas, a celestial body stripped down to a core of pure helium. This theoretical world represents a final, ghostly stage in the life of some hot Jupiters. The process begins with a star's relentless fury. Intense ultraviolet radiation bombards a gas giant orbiting far too close, its energy specifically tuned to break the gravitational bonds holding the lightest element of all, hydrogen. Over billions of years, this relentless stellar wind acts like a cosmic filter, selectively blowing the hydrogen away into the void while the slightly heavier, more stubborn atoms of helium are left behind. The planet's atmosphere becomes a shrinking envelope dominated by this inert gas, a pale blue bubble slowly deflating under the stellar glare. This helium world will be profoundly different from the hydrogen giants we know. Its atmosphere would be significantly lighter, causing it to puff up to an even larger size for its remaining mass, like a balloon filled with a magic gas that refuses to be weighed down. Its color would shift from the familiar bands of tan and orange to a softer, more uniform pale blue, the signature hue of scattered helium. The weather on such a world would be alien and subdued. Without complex molecules like methane or water vapor to drive intricate chemistry, its skies would be clear and serene, a vast, calm expanse of blue above layers of dense helium fog. The planet would be a quiet, almost elemental place, a stark contrast to the violent, storm-racked cloud decks of Jupiter. It stands as a cosmic fossil, a nearly final state in planetary evolution. After the hydrogen is gone and the helium atmosphere itself eventually erodes away, all that might remain is a naked, super-dense core, the burned-out heart of a former giant. This helium planet is more than just a 35th entry on a list. It is a glimpse into the ultimate fate that may await many worlds, a silent, blue testament to the transitory nature of even the largest planets in the unforgiving flow of cosmic time. These worlds of burning ice and diamond hearts have remained mysteries only because our eyes were not sharp enough to see them. The next great leap in understanding will come from a new generation of cosmic observatories, machines designed not just to find planets but to dissect their very essence. The James Webb Space Telescope is already leading this charge, its golden eye tuned to the subtle art of atmospheric spectroscopy. When a distant world passes in front of its star, starlight filters through its atmosphere. Each gas in that alien air leaves a unique fingerprint on the light, a barcode that Webb can read. It is already searching for the signatures of water vapor, methane, carbon dioxide, and even more complex organic molecules, turning the faintest whispers of light into a chemical profile of worlds light years away. But Webb is just the beginning. On remote mountaintops, a new era of ground-based astronomy is taking shape. The Extremely Large Telescope, or ELT, will gather starlight with a mirror nearly 40 meters across. This colossal eye will have the power to do something once thought impossible, to directly image the faint, warm glow of an Earth-like planet next to its brilliant star, separating its delicate light from the stellar glare for the very first time. This is not just about detecting atmospheres, it is about mapping surfaces. The ELT could one day chart the continents and oceans of a distant world, seeing the pale blue dot of an ocean or the green blush of a potential biosphere. The ultimate goal, however, lies with a planned mission called the Habitable Worlds Observatory. This space-based telescope is being designed with a single, profound purpose: to find and analyze at least 25 planets with signs of potential habitability. It will block out the light of their parent stars with a device called a starshade, creating an artificial eclipse that reveals the planet in stunning detail. By combining the powers of these observatories, we will move from speculation to knowledge. The flat, featureless spectrum of a shrouded water world like GJ1214b will be decoded, revealing whether it is a global supercritical ocean or a world with a heart of hot ice. The missing methane on the pink world GJ504b will be explained, uncovering the turbulent atmospheric chemistry that scrubs it clean. We will learn if the TRAPPIST-1 planets are barren rocks, global oceans, or shrouded ice worlds. Most importantly, we will search for biosignatures, combinations of gases that should not exist together without a biological engine to replenish them. The discovery of oxygen and methane in an atmosphere, for instance, would be a powerful hint of life, as these gases rapidly destroy each other without constant renewal. These tools are not merely bigger telescopes, they are keys designed for specific locks. They are the instruments that will finally turn our catalogue of mysterious, hypothetical compositions into a definitive atlas of alien worlds, revealing the true nature of the cosmos, one atmosphere, one ocean, and one continent at a time. From diamond hearts to cosmic cotton candy, these 35 worlds reveal a universe of staggering variety. Each one is more than just a strange new place. It is a direct challenge to our understanding of physics and planetary science. The profound darkness of TRES-2b forces us to ask what chemicals can swallow light so completely. The impossible lightness of the puffy giants defies our models of gravity and heat. The reigning metal of WASP-76b rewrites the book on alien weather. These are not mere curiosities, they are active experiments conducted on a galactic scale, each one a doorway to a new chapter in cosmology. The search for their true compositions is far from over. It is accelerating with every new observation from our most powerful telescopes. This journey through the cosmos reminds us that our own solar system, for all its wonders, is just one humble example in a gallery of infinite possibilities. The next time you look up at the night sky, remember, it is filled with worlds stranger than any fiction. If you enjoyed this voyage to the edges of known science, please like and subscribe for more journeys into the unknown. And we would love to hear from you. Which of these mysterious exoplanets captured your imagination the most? Let us know your favorite in the comments below.